Hi guys, hope all of us are doing great. My name is Ernest. I'd like to welcome each and every one of us to my channel of Ernest Sciences and Mathematics TV channel. Today, as our usual discussion goes, we are going to look at Gauss law and electric flux. And of course, we are going to look at the relationship that exists between the fundamental areas that we have looked at in the electrical field, the concept of charge, and of course, the resulting force that is going to be experienced insofar as charged particles are concerned. So basically today our main objective is to try and figure out the relationship that exists between these specific charged particles and how we can be able to characterize the resulting force and perhaps the electric charges that are going to be interact in order to create these specific forces. Now, of emphasis is the concept of the relationship between this electrical field and the charges, as I've said. And of course, we're going to consider the region in space that we call, of course, a region of influence that is going to be experiencing this particular electrical field. So that is going to entail, of course, the concept of a Gauss law and the concept of electric flux, which basically form our discussion for today. So basically, in trying to look at this, we're going to consider and appreciate the work of this German, of course, mathematician and astronomer by the name Carl Friedrich Gauss, who came up with various concepts in different fields. Of course, we're going to see some of its contributions in the study of basically electricity and magnetism. Hope my handwriting is legible. This is his contribution in electrical and magnetism, the probability theory, and of course we're going to see other contributions of Friedrich Gauss in other areas of geometry and even astronomy, which are going to play a fundamental role in development of related fields for this concept of electric fields. So therefore, having stated that, we're going to look at one of the concepts that he advanced in the topic of electricity and magnetism, and that basically is going to fall under the category of topic under discussion for today. So going forward, we're going to see that this Gauss law and the electric flux are going to assist us in trying to find a way of trying to describe electric fields in highly symmetrical objects, or rather particles that we had, of course, considered in our first case under the discussion of electric charges and other areas. So it's also going to provide for us an alternative for trying to, of course, create expressions or mathematical representations of the inverse square nature of electric fields. So in this concept, we're going to find ways of trying to describe the inverse square nature of electric fields as we go ahead, specifically for point charges that we have already looked at in some of our videos. So under this concept, we're going to look at the concept of an electric flux. And of course, I'm going to use an illustration in trying to give a figurative way in which we can be able to interpret this concept of electric flux. So on the board, I've given two rough sketches of our services. And one of the services on my left, of course, is a flat surface where this other one is curved. So in this specific case, I've mentioned the concept of a region in space where this electric field is going to be experienced. So for us to try and create a way in which we can be able to illustrate this Gauss law, or rather try to quantify it, then therefore we're going to consider this aspect of an area in space and try to see how we can be able to quantify that. So if I can try to remind ourselves of the previous concepts that we had looked into. In one of our videos, we had defined the concept of a Gauss law as basically ratio between charge and permittivity in free space. So I'm just going to give you just an illustration for that. So we have given electric flux, or rather the Gauss law, as the ratio between the charge and the permittivity of free space that we had given as Q over epsilon. And then this is, of course, we have said that this is a Greek letter phi that is going to represent this specific electric flux. And therefore, we are going to see it being a ratio between this one and this one. And therefore, from this, we can be able to define or state the Gauss law as the electric flux through a closed surface. Of course, we're going to look at the concept of Gauss surfaces, and this, of course, is going to be the electric flux through surfaces that is equal to the total enclosed charge divided by electrical permittivity in free space. So therefore, this is going to create a ratio that is going to assist us to define the concept of a Gauss law. So having said that, then therefore I'm going to use this illustration and try to create that figurative illustration that I've talked about, specifically on the concept of electric flux. So the concept of electric flux basically involve what we call this specific service. Let's give the area of this service as A, and then we are going to consider the number of vectors which represent the electrical field lines that are passing through this specific service. And this is going to create what we refer to as electric flux. So I'm going to give just an illustrative way. Now in our particular example, let me give this one for A illustration. We just give illustration 1 and 2 to create the contrast from this. So for illustration 1, we're having a flat surface that consists of area A, and we're finding that there is a number of vector, vector values of these electric fields that are passing through this particular surface, and therefore this is what we refer to as, electric field lines that are passing through these points on the surface of this particular illustration. So in this case, we have considered a flat surface, and we're going to see that in our assumption, we're going to make this assumption that the electric field lines that are passing through these ones are constant vector units, and therefore we are going to assume that we can be able to illustrate this particular, electric flux from this concept by trying to consider, the electric field and this particular area which we have given as a flat surface, by creating a relationship between this area and the, this area and the vector values of the electric field which are being experienced in this particular case. So therefore, if this is what we call the vector values for A, we can create a mathematical expression that is going to represent this particular relationship, which basically represent an electric flux, which is going to be given as A. So basically, this is going to be what we refer to as a scalar, and it's going to have units of Newton meter square per coulomb, and therefore this is going to be one of the ways in which we're going to represent it. In an hypothetical case, we're going to see that this flat surface is not normally what we encounter, since this surface, as we have assumed to be flat, is not going to be contained as a flat surface, and basically we're going to encounter some cases whereby we're not going to have a flat surface, and the electric fields units which we have assumed to be uniform are not going to be uniform. Therefore, for this particular illustration for number 2, we are going to consider surface that is curved, and how we can be able to represent these specific electric fields, which of course we have said are not uniform, and therefore the specific area which is of course curved and not flat as such. Now in this specific case, then therefore we are going to consider that we can find divisions of this specific area, which are very small units, by dividing them into squares and trying to illustrate these specific units for electric field and assume them to be constant. So at this specific point, we are going to have an electric field which is going to be assumed to be E with I, and then we are going to have this specific point. Yet we are going to have what we call an area that is going to be, of course, indicated using that. So this for a single square, and then if we try to find for another one, again we're going to consider, we have said that these are similar square units, so therefore we're going to have also a vector field that is going to be represented as such, and another area as such. So for us to find the total flux, then therefore we're going to consider the summation of these electric fields and this specific area, and that will invoke the use of the concept of calculus, as we are going to see later in our discussion. But in our first case, as I mentioned, we had assumed that this particular area is flat, and as an area vector A that is normal to the surface and of magnitude, of course, that we are given as A. So if you try to consider that this interaction between this representation, of course, is going to be given as the area, and just going to leave it as this, the area and particular electric field, and it's being given at a specific angle theta, then therefore from our general illustration of the expression that we have given, we're going to see that for such a surface, the electric flux is going to be given in consideration of this specific extension for an angle, where phi is going to be a scalar that is going to be given as a the cosine of theta in consideration of this specific angle, whereby theta is going to be the angle between E and A. So therefore for this specific surface, therefore, we are also going to see how we can be able to represent. So for a flat surface, it's going to be given as EA, but for this specific extension for an angle for the electric field and the vector that we have given for A, for the vector E and the area that we have given for A, then therefore we're going to have this general representation. Now, for the second case, if we consider that we are having this specific electric square, and then we denote it by I, and then therefore we're going to represent this electric flux as, of course, this specific individual contribution. It's going to be the flux of I, E, I, as that. So therefore, from this, we can be able to find a relationship that is going to be used to express the electric flux of this whole area that we have given as a curved surface. And therefore, as I said, this is going to entail the use of the concept of calculus, which basically is going to give an impression of the summation of these whole areas of this particular surface and then the electric field. And therefore, from this, we can have a general representation that is going to imply the electric field being given as a summation from I over this specific area, and the electric field that is going to be given as this for individual elements. So the summation of all this will make up the general expression for the electric field. So basically, this is going to give an integral form of for one variable, and we can borrow from this specific concept for the surface integral and find a particular illustration for the electric flux over this specific surface, which is basically going to be given as the electric flux is going to be the summation of this surface for E, dA. And of course, we are going to borrow from some of the mathematics concepts that we have looked at. I'm going to put a link in the description box for the integration of services or integral of services, of course, which is going to assist us in trying to interpret the integral of services for this specific concept. Therefore, in summary form, as I've said, the Gauss law and the electric flux, of course, are going to create a relationship that is going to assist us, of course, relate electric fields that we're going to experience of particular regions in space and the charges that are found in that specific region. And this specific concept is important for us in trying to understand, of course, electric fields of charged objects, especially for symmetrical objects, as I've mentioned, using this illustration for the two illustration for 1 and 2 for flat and curved surfaces respectively. And this, of course, is going to give an alternative way of trying to express what we refer to the inverse square nature of electric fields, especially from point charges that we have discussed in some of our videos. And of course, this is going to give us a numerical way in which we can be able, or rather analyze the electric flux that we have given or represented in different ways, for this specific one that is normal to the surface and the one that is extended at a particular angle for E and A that we have given as theta. So therefore, we say that in normal cases, we're not going to have these flat surfaces and then a uniform electric field as we have assumed in our first case. And therefore, we're going to consider a curved surface for this specific sense for this specific area that I've given. So for us to try and analyze this one, we're going to consider dividing these specific curved surfaces in small squares, which are going to assume are flat, and the specific electric fields for these individual squares are going to be uniform. Therefore, for us in enumerating the total flux in this specific surface, we're going to use the concept of calculus, which is going to basically entail the summation of these individual squares in order to find the total area of that electric flux of that curved surfaces. Now, this is going to lead us to another concept that is going to assist us interpret the concept of Gauss surfaces. And we're going to look at the concept of a symmetry that I've already mentioned, which basically is going to assist us in trying to find, or rather trying to define other areas, especially that we're going to find in capacitance and other areas that entail the concept of electricity and magnetism. So catch us in our next video where we're going to look at the concept of Gauss surfaces and other related areas. So that is it for now, guys. Bye. God bless you.